I think it works.
Okay, thanks. Thanks for having me here and in this seminar. So yeah, I'm Meng-Xiang. So oh yeah, right. So yeah, a bit more about myself. If you missed my intro in the Jamboree last Friday, so I just briefly repeat a little bit again. So yeah, I'm interested in theoretical cosmology. So mostly I'm working on the new physics behind the cosmological tension, which I will talk about today. And also I'm interested in testing gravity with gravity wave and the enthalpy of the gravity wave background. So if you are interested in those topics, also welcome talk to me. I will be here until Friday. So yeah, okay. So yeah, today I'm going to talk about the cosmological tension and the possibly new physics behind it. So I believe everyone knows this. You've seen this picture for many times. So now we have standard model for cosmology called lambda CDM. It's required a particle physics standard model plus our theory for gravity, which is general relativity, plus cold-dark matter, and cosmological constant called lambda, and inflation. So let's we'll explain how the universe is born from a Big Bang after inflation, and how it evolved until today. So it's I would say a very successful model. It explains many different cosmological observations, like CMB you see here, the structure formation, large scale structure, and BO measurement, supernova measurement, galaxy surveys, kind of standard paradigm for current cosmology. But there are still, from theoretical side, two fundamental mysteries. So we know in lambda CDM, our universe, in terms of the energy budget, we have 5% of the ordinary matter. We usually call it baryon in cosmology. We have about 25% of dark matter, and 70% of dark energy. But we only have a good knowledge about this 5%. Okay, we have no idea about what's the nature of this 95% of the dark sector. So let's I think the two most fundamental mystery in the modern cosmology. So keeping this theoretical mystery in mind, if you look at the observation, okay, we also have some observation hint that it could be some possible deviation from lambda CDM. We have the recent dynamical dark energy evidence, SA tension, hypotension, and also cosmic birefringes. So today I'm going to talk about the first three, but not the last one. But here is my outline. So I will first give a brief review of the current cosmological tensions from observational side, and then I will introduce the dark matter interaction. So particularly, I will introduce a particle physics model that we propose about dark matter energy interaction that can give the apparent phantom crossing behavior that can explain the latest static result, and also explain the SA tension simultaneously. And after that, I will talk about the hypotension and the possible solution to that. And well, in the end, I will talk about the future track to all of these cosmological tensions. So let me begin with the dynamic energy. So some of you may already seen this before in this year, but let me repeat it again. So in March this year, so DAISY released their data release 2 result and give evidence for the dynamical energy. So this is posterior for the equation of state of dark energy. So you can always parameterize the equation of state as whatever function. So this is usually people doing. So in lambda CDM, this equation of state of dark energy is just -1. It's constant. Right? So we call it cosmological constant. So that's the point here. But if you allow the dark energy to be dynamical, so you can, the simplest parameterization is you use W not WA parameterization. So you see it's simply just a Taylor expansion as function of the scale factor A. So by doing this, if you fit to the data, you will see it's deviated from the constant. So the biggest evidence coming from if you combine DAISY without CMB and supernova is, for example, the DAISY DR2 plus Planck CMB plus DS EF5 supernova give you 4.2 sigma, which is yeah, this one, green one. So so that's exciting, but I think it's important about DAISY DR2 compared to DAISY DR1. The result looks more robust to me. So in DAISY DR1, you already see some evidence about 3 sigma-ish for this dynamical dark energy. But if you look at DAISY DR1, you take away the supernova data, you will find almost all the signal of the dynamical dark energy just gone. But now, if you look at this, the dash control, it's just about DAISY plus CMB without supernova. You still get 3 sigma-ish evidence for the dynamical dark energy. So to me, I think that's much more robust. Usually, okay, people will thought CMB and BL are more robust. But you don't know what people always worry about supernova observation. You don't know if there's some unknown systematic or no. But now you see, even without supernova, you still get 3 sigma evidence. So that's much more robust. And also, for sure, if you add the supernova data, you get higher evidence. So let's say something at least. So also particularly interesting, if you look at the DAISY result, you will see the equation of state of dark energy. It's less than -1 in the past, and higher than -1 today. So it will cross -1 at about redshift 0.5. So this equation of state less than -1 is particularly interesting. So so this orange line is the W naught WA fitting result. So as I explained before, W naught WA is just a simple Gaussian expansion. It's not a physical model. So it can easily break down if you go to the deviation is too much from lambda CDM. But instead of this simple parameterization, editing also use Gaussian process method. So that's the blue shade you see here. It still shows that in high redshift, the equation of state is less than -1. So that make the evidence for the W less than -1 result more robust. So now, yeah, this is another independent method to get the evolution of the equation of state. So this is from the reconstruction result. It has a less constraining power, but still you see the result cross -1 at some point. So you will ask, what about without daisy? So this is a result from the DS. So if you look at this orange contour, it's the DS BL plus DS supernova plus CMB. Without daisy, you still get 3 sigma-ish evidence for the dynamic technology. So I would say for now, it looks very possible that we may need the dynamic technology to explain the latest observation. Okay, so now we go to the theoretical interpretation. So why this is interesting, particularly interesting when you have the W less than -1. Okay. So for usually for W larger than -1, we call it quintessence. So that's the normal scalar field model will give you. So as a normal scalar field, you always expect the equation of state should be larger or equal to -1. So for equation of state less than -1, people give it a name called phantom field. Okay. But now we saw some evidence for the model to cross -1. So for a single field, you cannot do that. But there was some proposal 20 years ago. You could have a two model to realize that. But the problem is this so-called phantom field model is dynamically unstable. So if you have the equation of state less than -1, that means the density plus pressure will be less than 0. So just remind the definition of W is just pressure over density. So P over rho less than -1. So if W less than -1, you will violate this non-energy condition. So this non-energy condition are usually expected to be true in most of the normal case. So W less than -1 means violation to this non-energy condition. So if you violate the non-energy condition, it's almost inevitably imply some ghost or gradient instability, or you have some luminal propagation. So either of this is not healthy. So in theoretical point of view, so it's a challenge to explain if the evidence for W less than -1 is real. So what happened? So there are some possibility of the stable solution. We call it the parent phantom energy. So there's some proposal through it's all through some interaction between the energy and something else. It could be interaction between energy and the gravity. That means modified gravity. Or energy interact with dark matter. That's what I'm going to explore today. Okay. So regarding about the dark matter energy interaction, okay. Before I drop to that, I will talk about another cosmological tension that you will see also give us some hints that maybe there is some dark matter dark energy interaction. So let's call it SA tension. So this is tension between the early universe measurement from CMB and the late universe measurement about the galaxy survey. So it's characterized by the amplitude of the matter clustering. Usually, people use the S8 parameter to characterize it. So this is an example from BSEA3. You will see about 2 to 3 tension between these. So not only BSEA3, so it's also come from another survey. So here is a kind of summary. You get the measurement of asset value from CMB, FANC, SPT, ACT, and CME lensing. They are all kind of higher than the local galaxy survey from different independent survey. So anyway, it's not a big tension, it's only 2 to 3. Maybe not real, I don't know, okay. So, but keep that in mind. So, it has been there for decades. So, earlier, I have a simple phenomenological model about modification to the late time growth. So with Wolf Jane and Mark Rivalry. So it's not a physical model, but so it's just a simple phenomenological model to explore if you can solve this SA tension with some simple modification to the late time growth, and the answer is yes. So it seems that what you need to solve SA tension just suppress the late time growth in a very low redshift. So interestingly, you will find a coincidence between the dark matter dark energy equality time, which is about redshift 0.7, and the separation of the lensing kernel between the galaxy lensing and the CMB lensing. So CMB lensing and galaxy lensing, they give different SA value, but they all lensing effect. The only difference is they pick a different redshift. So galaxy lensing is sensitive to a lower redshift. So if you just suppress the structure growth in low redshift, you kind of solve the SA tension. So that's what we did. So if you have this simple modification, you can find, oh yeah, SA tension kind of been solved. You get like 3 sigma evidence deviation from lambda CDM. So that's what we have using the DS data. And yeah, this model is also analysis by other independent collaboration team. For example, Eurostat analyzed our model with their Eurostat survey, get 4.4 sigma evidence, and also HSC, Subaru HST, they also get about 2 sigma evidence for our model. But anyway, this is not physical model. So what we learn from that is just, yeah, a simple suppression of the structure growth in late time can solve that. But what can cause that? The possible underlying physics could be if you have dark matter dark energy interaction. Okay, so somehow you may impact the dark matter clustering in the epoch that dark energy can dominate. So that may be another hint that, okay, the interaction could be there. So given all of this, so yeah, we have explored the dark matter dark energy interaction. So with Justin and Mark, we wrote a paper right after DAISY. So about such an interaction. So we have concrete particle physics relation through dark baryon and Meng-Xiang interaction that I will explain later. So with this model, we can explain both the phantom crossing behavior that we saw from DAISY and SA tension simultaneously. So let me explain it. So far, is there any question? Okay. Right. So before I talk about the concrete model, let me take a few minutes to talk about the naturalness of the dark matter dark energy interaction. So for sure, this is this topic has a long history study. So there are already many work talking about this. So there's usually a question about the naturalness of this. So usually this coupling will give a large radiative correction to the dark energy mass. So, but if you need the dark energy to drive the acceleration expansion of the universe we saw today, the mass cannot be very large. So the mass should be small, so it can behave a kind of slow-roll-like behavior. So that will lead to the acceleration expansion. So you want to avoid this large radiative correction. Okay. So there's a well-known exception for this, which is epsilon. So due to the discrete shift symmetry, so if you have the if your potential is axion potential, you can avoid this large radiative correction. But for the axion potential, you have another problem. Usually, it's another problem. So usually, people thought the axion only coupled to matter just derivatively, but so that doesn't really help. Okay, so the normal derivative coupling not help in the to realize the phantom crossing behavior. But in today's talk, I'm going to show that we have in our model, the axion will depend on the matter density, not derivative, the density itself, in the exactly right way we want. So I will show that. So yeah, this is our model. So in our setup, we have the dark matter to be another dark sector of dark baryons. So the baryon is the standard model. So we have another dark sector. So it's dark baryons. So this is also a natural candidate for the self-interacting dark matter that people have explored for a long time. Okay, so just like the story in the standard model, so if you have this another dark sector, you will have an associated dark QCD axion to this dark baryon. It's just similar to the standard QCD axion that people expect in the standard model. So, the potential you can ignore the formula, but anyway, so if you are not familiar, you can ignore it. I will show the potential later. But if you are familiar with the axion potential, so here it's not exactly as the cosine formula that you usually see. So it also depends on this the z parameter, so which depend on the ratio of the quark mass. But in the case that the quark mass of upper quark and down quark are equal, this formula just reduced to cosine. So you can see here, if this is 1, 1 minus sine square is just cosine square. So it's a cosine potential, usually the usual axion potential. Okay. So the key difference between this dark axion potential, QCD axion, and the standard QCD axion is about the energy scale. So here we want this dark QCD axion to serve as dark energy. So it's going to be a scalar field anyway. Okay, so the setup is again, so our dark matter is dark baryons. Our dark energy is a scalar field that associated with the dark baryons from the dark QCD axion. So we want this scalar field to serve as dark energy. So we want this energy scale to be the Hubble scale today, because we measure that. Okay. So this is a requirement. We don't explain why it's milli-eV, but because we know the Hubble parameter today, so we require it to be milli-eV. So this is very different from the standard model. In the standard model, the energy scale is about mega-eV. So, but we have milli-eV, so that's the main difference.
But
yes?
In both models, you have the same Hubble parameter locally, right?
Yeah, we only have one Hubble, local
right,
Hubble.
Exactly. So why would you expect two different energy scales?
Oh, because the standard model QCD axion has nothing to do with Hubble.
Okay.
Exactly because it's too heavy, so it cannot behave like a dark energy. So usually people have some proposal to make it behave like dark matter, but never dark energy because it's too heavy. But here we want it to behave like dark energy, so we require it to be light. Okay. So right. So also we have a relation between the energy scale and the pion mass and pion decay constant. The thing is we introduce epsilon parameter here, and we require the epsilon to be much less than 1. So in standard model, this parameter is 1. Okay, this is 1. But we need it to be less than 1. I will explain why later. So these are the difference. And also this, because it's small, so we can set the energy scale to be small compared to the standard model. So that's the key difference between dark sector and the standard sector. Yes?
Does this mean your confinement scale is small? So shouldn't this set the mass?
Good. The confinement scale could still be large, but there is a kind of, you need a hierarchy between the confinement scale and the energy scale here. So that's why you need this.
But these models, like the kind of long models, requires adding many copies of the standard model. That's how you
Right. That's one possible way to do that. Yeah. Well, you may have. Well, I don't know. We are working. Well, I will talk about later. But you maybe possible have another realization. We have this epsilon to be small. But yes, many copies is one of the possible way. Yeah. Okay. So right. So given this setup, the dark matter dark energy interaction will just naturally come in from an effect that already known in standard model. So it's coming from correction to the quark condensation in the finite baryon density case. Okay. So let me explain that. So yeah, you can. It's a well-known relation between the quark condensation and the pion mass and decay constant. So remember, so this quantity is proportional to the energy scale. Okay. So and it's equal to the quark condensation. So in the finite baryon density, the quark condensation will receive a correction. So it's just expansion in terms of the baryon density. N is the baryon density. So in linear level, it's just the correction is proportional to the baryon density. Okay. So, but here our barrier is dark barrier. So that means the correction will be proportional to the dark matter density. So that means if your dark matter density is not zero, you get a correction to here and to here. So to here. So you get a correction to the dark energy scale. So or the amplitude of the dark energy potential. Okay. So this is the correction you get. So you will find the correction has the exactly same format of the axion potential. So in N, you find your axion potential will depend on your dark matter density. So in the end, effectively your dark matter mass now will depend on the scalar field. So that means from cosmological point of view, your dark matter mass is evolving. Okay. So as the scalar field evolves. So I will show later that you will see this is the dark matter mass. It gets a correction proportional to this sigma n parameter. That's the pioneer sigma parameter in standard model. So this means it's a derivative of the quark mass to the nuclear mass. So usually you will expect the heavier quark mass, the heavier nuclear mass you will get. So this parameter should be expected to be positive. So if it's positive, you will see the dark matter mass is increasing as a function of time. So that's what we want. I will explain. Okay. And so this is to give you a picture of how this model works. So the total effective potential is coming from bare potential plus the correction I showed before. So okay, so without any coupling or without any dark matter, the bare potential just this blue line. It's kind of cosine-like potential. So if the dark matter density is non-zero, you get a correction which have the opposite sign to this. So that means in a very early universe, when dark matter density is very high, you flip the potential. So this is the potential looks like in very early universe. So as the universe expands, the dark matter density goes down. So the potential will kind of become flatter. And at some point, the dark matter density crosses the critical density, the potential flip. So this is the potential looks like from the early universe to today. Okay. So the field evolution will be at the beginning. You can start your field at any position, but you see there's a minimum here. So the field will always go to the minimum and stay here for a while until at some point the potential flip and the potential will start rolling down. So it's kind of in the slow roll phase, which drive the acceleration of the expansion of the universe as we saw today. So that's the whole story. So these potential flips should happen at dark matter and the dark energy equality. So that's a special timing. So when this happens, that means the bare potential should be comparable to the correction. So the bare potential is the scale of dark energy as required, and the correction should be proportional to raw dark matter. So that means the critical density should happen at the epoch that these two energies density be comparable. So let's dark matter dark energy equality, which happened pretty much recently, I would say. Well, depending on the concrete parameter anyway, but in our working model, it's happened at about redshift 4 or 5-ish, pretty recently. Okay. So this is the whole story. So yeah, this is our working model. So at the very beginning, you can start anywhere. So you roll into the minimum and stay there for a while until pretty recently, redshift 4 or 5-ish, and you start rolling. So this case is the dark energy dominant epoch that we saw today. Okay. So okay. Any question about the evolution so far?
I guess my question is, if the equality happens at redshift 4 or 5, that would there be, how much difference would we expect to see in terms of, say, high redshift galaxy properties before that equality redshift and after that?
Galaxy property.
Yes, I was just wondering if there's any, for example, the clustering of galaxies.
Oh yeah, I would say that.
Okay.
Yeah, I will explain that. So
Thanks.
it should be impacted the clustering. Yeah. Okay. Right. So right. Yeah. If no more question, okay. Now I can jump to the phenomenology. So maybe for people close to the observation, maybe, care more about this. So yeah. So the first is about the phantom crossing. Okay. So let me explain how we get the apparent phantom crossing. So remember, so in our model, the dark matter mass is varying. So as I said before, so the dark matter mass is increasing. Okay. So that means the dark matter density is also evolving. So well, in our model, the dark matter number density is still conserved. Okay. So in the standard lambda CDM, so you get the low dark matter proportional A2 minus 3 because of the expansion. But now, because the mass is evolving, so the total density should be proportional to the mass itself. So because the mass is increasing as function of time, that means in early time, the mass is lower. So the density should also be lower. So compared to the standard cold dark matter, this is roughly, it's just for illustration. In the early time, your dark matter density is also lower. So if you fit the data assuming a constant cold dark matter without knowing this interaction, and you would assign this missing part of the dark energy to dark matter. A missing part of dark matter to dark energy. Okay, so you assume you have cold dark matter plus whatever dark energy. So this is exactly what DAISY people doing. So you find, so your dark energy density will get additional contribution from this missing part. So you see, as long as this additional contribution is less than 0, you will get an effective equation of state of dark energy to be less than -1. So that's how you get the phantom behavior. It's an apparent phantom. So just because you fit the data without knowing the interaction, but just assign this missing part to dark energy, you call it whatever evolution layer to be dark energy, but it's not really. Okay. So right. So for concrete, to be concrete, you can write down the effect W as function of your dark matter mass, and you find if dark matter mass is increasing, you always get this. So this is kind of generic statement. You don't even need to realize with our particular model. So our particular model can realize this, but you can also realize this by maybe the other possible model. If you want to explain the apparent phantom crossing. Okay. So anyway, so in this explanation, there's no real phantom field. So the apparent phantom crossing behavior just because you assume a standard non-interacting dark matter. But if there is, so you get this. Okay. So right. So this is we give we give two working examples actually for our model. Okay. So this is the equation state. And so for these two working examples, you will see you have the equation state less than -1, cross -1, and about ratio 0.5. So so yeah, if you map this to the W0 WA diagram I showed before, so it will be in this corner. Oh yeah, I didn't show that, but yeah, it will be W0 larger than -1, WA less than 0. So in the corner that the density contour show. So but anyway, compared to this result from density, you will see more or less look similar. We haven't did the careful likelihood fitting. So this is just a working example. I just choose some parameter to illustrate that. So you will see it could be explain the result. Okay, and before I talk about the clustering, let me give a few more words about the naturalness of this model. Okay, so first, let's know fine-tuning problem here. So the field could be started from anywhere of the potential here because of this potential flip. So it doesn't matter. So as we show here, you could start anywhere. So no initial fine-tuning thing. Also, it gives a kind of initial condition for the axion potential to behave like dark energy. So that's a well-known tuning problem if you want axion potential to be dark energy. So that means you always need to set your potential near the top of the axion potential. So it can slowly rolling down and driven the acceleration expansion. But why it's initially almost on top? That's a tuning problem. But in our model, because let me show you more. So you usually need to place the field here, so it can roll it down. But here, because of the potential flip, this maximum was a minimum at the early time. So that will naturally give you a reason why it starts from here, because it's a minimum before, so it's always rolling to a minimum and stay there for a while. So that will also explain the well-known problem for the axion energy. Okay, and also dark matter dark energy equality is special timing as explained before, and there's no radiative correction and stable imperturbation. So far everything looks good. So the only thing may need further explanation is the small parameter of the epsilon, as you mentioned before. So we remember this epsilon. So it's between the energy scale and the pion mass and the gain constant. So in standard model, this parameter is 1. So you don't need any explanation. But here we need it to be, well, let's say more or less than 10 to minus 12. So one reason is we want to set this energy scale much smaller than the standard energy scale. That's kind of related to the cosmological constant problem, but we cannot explain that yet. We do not explain why the cosmological constant is so small, but we just require it. And also, it's also a requirement for the perturbation to stay in a linear region. So the linear perturbation do not break down. So that also require this parameter to be small. All of these requirements kind of in the end coincide in the same parameter requirement. And as I say, there could be some realization. We're still unsure about it. It could be through some like multiple copy of the standard, maybe not standard now. So multiple copy of the sector will realize that. Or we have some other idea, but we're still working on it. But this small parameter is different from standard model. Looks maybe not that natural, but I would say it could have some natural realization, but we are not sure for now. Okay, so I've explained the phantom crossing behavior. Now, what about the linear density growth? So there are two effects here. So first, because the dark matter mass is lighter at an early time, so we will shift the matter radiation quality to a later time. Okay. So and we know the matter density homogeneity start growth mostly in the matter dominant epoch. Okay. So if you shift the matter radiation equality to a later time, you will delay that growth. So that means the matter clustering you see today will be lower. So roughly speaking, in terms of density in homogeneity, the C, the ratio should be proportional to the mass at equality. Mass of the dark matter is equality. So this lower the density growth. And the other effect is now you have a different expansion history in the dark matter dominant epoch pretty much today. So roughly speaking, if you have an increasing W effective, as we saw from DAISY, genetically we have a growth suppression. So this has another suppression happened recently. So both of these goes in the same direction that we want to suppress the assay tension, suppress assay value. So we know in low redshift we want the assay value to be lower. So it just turned out that the requirement for the DAISY result and the assay tension goes in the same direction. So all you need is the dark matter mass is increasing. That's the key. And of course, there's a third effect if you think carefully about it. So the interaction between to the dark energy will mediate a fifth force between dark matter. It's a scalar field induced fifth force, so it's always an attractive force. So this attractive force will always increase the matter clustering, which go to the opposite direction. Okay, but the story is it turns out it could be subdominant because this effect is proportional to the quadratic term of this derivative. So it's not necessary to be subdominant. You see, here it's a linear term in the mass effect itself, but this is quadratic in the derivative. But fortunately, in our model, we show that it is subdominant. So this third effect go to the opposite direction, but it's subdominant. So still these two effects are dominant. So in the end, you still get to the suppression of the matter clustering. So this is what we get in N. So so this is just a fractional change to the cold matter. Now it's not cold matter anyway. The dark matter density homogeneity. So we see you get a first suppression. This is you shift the matter region equality, and you get a second suppression in the energy dominant epoch. So in the end, roughly speaking, you can have you suppress the matter clustering and also the SL value in the end. So let's go to the right direction. Okay. So that's how this model can also explain SA tension compared to Meng-Xiang. So if I finish to talk about this model, I have some remarks on the parameter choice. So first we don't have any tuning things here. So no worry about the initial position parameter. So the pop mass ratio we choose here, we fix it to be 0.8, close to 1. So kind of some natural choice. So decay constant is less than m Planck, which is also healthy. So if it's larger than m Planck, it's problematic, but without. So the interesting part is about the coupling parameter. Okay, so this coupling parameter, this sigma n is dimensional. So the thin matter is sigma n over the dark matter mass, the bare mass itself. So this is dimensionless quantity. So in standard model, you actually have the measurement of this parameter. Okay. So in standard model, from Collider, people measure this sigma n parameter to be about 60 MeV. And in standard model, we know the baryon mass is about the proton. Proton is about 1 GeV. So this ratio is about 0.06 in standard model. So we do know the number, okay. But in our dark sector, so the data prefer means it's not a real fit, but I just adjust the parameter to make this crossing happen at about 0.5. So okay. So roughly speaking, the data preferred number is about 0.1 to 0.2. So it just happens to be in the same order of magnitude. Kind of an interesting coincidence. I don't have an explanation to that. It's just kind of interesting. Okay. So I should point out here. So maybe not too crazy because in principle it could be anything because it's a totally different dark sector, right? It turned out to be similar. Okay, so yeah, so I will also mention there are some other paper after that. So there's also some realization from string theory about this dark matter dark energy interaction. So I'm not expert there, but if you are interested, you can look at the paper from Bafa's group and Gary Shu's group. They all talk about similar idea about realize this dark matter dark energy interaction scenario with string theory. Okay. So yeah, how many time for now?
We have like 4 minutes left.
Oh, okay. So well, maybe I will quickly just talk about this. So yeah. So yeah. So right. So you are the other interested in because you are asked about Hubble tension. Okay. So briefly introduce. So Hubble tension is between Hubble parameter measurement between the early time and the late time. So it's kind of 5 sigma tension. If you believe it's like measurement and Schu's measurement. So right. So right. So let's say I will skip this. So right, there are a lot of proposal about hypertension. So it could be late time proposal and early time proposal. So late time proposal turn out to not work. Okay, in general. So this is some list, maybe not complete now. About some proposal of the early time to the hypertension. So, for example, the early energy model that I also include myself. The basic idea is for early dark energy. So you have an energy injection around metal radiation quality. So you reduce the south horizon. If you reduce south horizon, but you still keep the the measurement of the angular size of the CMB peak. So that will infer lower distance from today to CMB. So that will give you a higher Hubble parameter. So right. So yeah, let me briefly explain it. So in CMB, you measure this angular size. So this is the ratio between south horizon and the distance. If you reduce this, you will just infer a shorter distance. And the distance is inverse proportional to Hubble parameter. So you infer a higher Hubble. So that's the basic idea of early dark energy. So so it's a proposal realized by the injection about metal quality. So you could realize it in many ways. So the simplest way is also a scalar field. You have the Renaissance scalar field. It just happens dominant about 10% of the energy budget here, and not here, not here. You get that? Okay, that's a simple idea. But in this model, there's some problem, right? So the early dark energy model itself will worsen the assay tension. Okay, and you will also have a theoretical problem why metal radiation quality is so special. Right, it's a kind of coincidence problem. But yeah, I've done several work about that. If you're interested, you can ask me later about more detail about that. But I don't have time to explain that. But what I want to say here is, okay, so what about the dark matter dark energy interaction model? Could that help on that? The answer is maybe yes. Okay, that's the interesting thing. So remember here, we also have the potential rolling at the early universe. So if you have the sun displacement at early time, maybe you get the early dark energy scenario for free. Okay, so that means in this model we already show it's good, okay for the phantom crossing behavior, it's okay for the assay tension, and for Hubble tension, maybe yes also. So we are still working on that. But if that works, that means you don't need to introduce anything else. You just get that for free. And also, there's no coincidence problem in this model because of the coupling to dark matter that we showed before. Right? So the rolling should trigger also by the coupling, and dark matter by definition would be comparable to Hubble at matter radiation quality. So that's already give itself a special timing. So there's no coincidence here. And also, yeah, if we don't know yet, because working on this, you need to fit to the likelihood to tell if that works or no. So we are working on that. So so yeah. I will stop here. So here is my summary. So so let's kind of more evidence for possible deviation from lambda CDM, but we don't have a perfect solution to offer that yet. But we're kind of on the road. Okay. So we propose an unstable and a technical natural particle physics model of dark matter dark energy interaction. So we show we can simultaneously explain the phantom crossing behavior for DASI and assay tension, and maybe also for Hubble tension. We are still working on it. So I already have the model implemented into class, so just we are running for the light quick for now. Okay. And for the future, for sure, the theory should be tested with the observation, right? So for future, we still have some ongoing and proposed experiment, both from CMB side and the galaxy survey side. So especially like for PFS, that's the galaxy spectroscopy survey. Compared to DESI, go to the higher redshift. That's particularly interesting for this model. If you try to see possible non-cold dark matter behavior, higher redshift will be interesting. Okay, so yeah, I will stop here. See.
Okay, we had a couple of questions already. Any other questions from the room?
Just so I understand,
Yeah.
back to you. So the break in phi away from pi times that occurs when you have the sign flip in the coefficient of the potential. Is that right? So you have, yes, go back. Sorry, go back.
Go back.
Go forward. Yeah, there.
Oh, okay.
Okay, so at low redshift, where you have the break in the plateau in phi,
Oh yeah.
that's occurring where this coefficient in front of the square root of the Meng-Xiang potential changes sign.
You mean this?
Get this feature here.
Oh, this feature is just when the potential flip, right? So
Yes, when the coefficient flips.
it's just randomly rolling to either this way or that way.
Yeah, but this is then related to the ratio of the vacuum energy to the dark matter or the dark baryon density.
There's still some dark baryon density.
Right, but I mean, well, so you have this coefficient.
Coefficient, you mean here?
1 minus sigma n
Yeah,
over
here.
lambda to the fourth, right? So can you clarify how that second term in that coefficient is related to the ratio of dark matter density to vacuum density?
Dark matter density.
So sigma n is
Oh yeah,
a
right.
combination
So
of
sigma n is the
some fraction of the dark baryon mass.
right. So if you write this n to be rho minus n,
Yes,
okay. Sigma n over m is the dimensionless
Right.
parameter.
right.
And that's kind of like order 0.01-ish. Okay. So
But it's not a coincidence in your plot of phi versus redshift that the break in the curve of low redshift is occurring when the dark matter density and the vacuum density are becoming comparable.
right, okay. If this parameter is, let's say, if sigma n over m is order 1,
Yes,
then the critical thing is this thing equal to 1, right? So
yes,
that means rho roughly equal to lambda to the fourth.
right.
Rho dark matter is dark matter density. Lambda to the fourth is dark energy density.
Yeah.
So if the parameter is order 1, that means this should be dark matter dark energy equality.
Right,
Yeah.
which empirically is occurring at some small redshift.
Yes. Right. Yes. That's why I say this special timing is coming from here. But in the concrete model, okay, concrete model we have this not
I know,
exactly model 1, but
You have a
the
small
specific model.
coefficient
Yeah.
in
It's
the
like
sigma.
0.01-ish.
But numerically, it's still, this transition is still happening
Yeah.
around where the dark matter density and the vacuum density are comparable.
Right.
And that wouldn't be the case if you chose a different coefficient than sigma n.
Yes, it will. If it's very different from 1, like very small. If it's very small, then you push it earlier. Right? So the critical density is happen here. It's defined
Sure.
here.
Sure, but I guess what I'm asking, okay, we make sigma n order n naught, okay?
Sigma-
Make it,
You mean larger than 1?
no, order naught.
Order naught,
n
yeah.
naught. Well, you take it to be a small fraction of n naught, don't you?
Oh, the value we get is about 0.02.
Yeah, right.
Yeah.
So if you took it to be
1.
1,
That will happen at a later time. So, because the equality roughly 1-ish.
okay, so then you would get a break in the curve at redshift 1.
Yeah, it's like roughly 0.7, roughly speaking. Yeah. So it push later time. So if you get the smaller, it push it earlier time. Yeah, but even the result will show that even the value will take a 0.02, it will push to the break at the redshift about 4-ish. That just give you a sense. Yeah, that's right. It depends on this coupling. Yeah.
Okay, cool. Let's thank our speaker again. And Meng-Xiang will be around all week in the visitor's office hanging out. And so if you have more questions, please do remind me. There are probably snacks upstairs, so go ahead and check so we can start on that. Thanks.